specific case studies. So the book will become very important. So we're going to talk about volcanoes today, and this is a picture of a stratovolcano, one of the 3 types that we will discuss. And I wanted to show you a couple things about this. First, these are the picturesque, big, violent, dangerous volcanoes that we're afraid of. In other cases, we're not so afraid of volcanoes. As you know, Hawaii, right? When a volcanic eruption happens on Hawaii, we run to it so we can take pictures of it and watch the magma. We'll talk about why, for this same phenomena of volcano, some are violent and dangerous, and others are quiet and kind of pretty to look at. But this, in the stratovolcano realm, what you should note about this is that there's a snow-capped peak. We'll see what happens with that snow. And then in the foreground, you can see stuff that kind of looks like snow, only it's not bright white. That is a lava flow. And in the case of this type of volcanic eruption, the lava's not flowing like you think of with Hawaii and with these rivers of lava going down the side of a mountain. It's this blocky, irregular, chunky stuff that kind of bursts out and appears, most of it, as rock already cool. So fragmented, angular stuff, a field of rocks that overall looks like it's liquidy, but it's almost cool. So we'll look at why that happens. So this is a summary slide. I have a slide on each one. We'll look at the 3 types of volcanoes: stratovolcano, shield volcano, and a cinder cone. The first one, stratovolcano, is, So the first one, stratovolcano, is the classic type of volcano that you think about. Violent, dangerous volcanoes, and they burst away and you get far away from them when they erupt. Huge amounts of ash coming out of this volcano, and we'll look at this in a film clip later on, maybe next week. They are characterized, I put this cartoon diagram with a cutaway in it, as having alternating layers of lava flows and then something called pyroclastic debris. Pyro is fire. Clastic just means broken rocks. We use the word clastic in sedimentary terminology as well. So broken up fire rocks, things like ash, chunks of pumice. So these layers, you see the blue-gray layers, what would happen is the volcano would erupt, and the first thing that comes out is the ash, and then the lava will coat it, and you have these ash-lava pairs, and in this way, most of the time, every time there's an eruption, the volcano will grow in size because you're adding material to it. In some cases, we'll talk about Plinian eruptions that are huge. The volcano goes off so violently and bursts away so violently, and you have earthquakes going on, you have all sorts of landslides perhaps, that the volcano will actually get destroyed. And I'll show you a picture of Mount Etna where it was partially destroyed by a very violent eruption. And in some cases, like Crater Lake out in the Pacific Northwest, a huge mountain went off so violently that there's nothing left, and it collapsed and filled with rainwater and formed a lake. But typically with these, you have ash lava pairs and it grows. So you see this cloud of ash and there's a lot of gas in it. This will be the most dangerous thing in a stratovolcano eruption. So these are also called composite volcanoes because they're made of those 2 things, ash and lava, ash and lava. It's possible to core down into the sides of these also. And by radiometrically dating the lava flows, you can tell about how often this volcano went off. So when we talk about different disasters, we'll talk about periodicity. Do they happen with a regularly spaced interval? And volcanoes aren't as regular as some of the other phenomena. Rivers flood with a real good periodicity. You can tell about how often a river of a given magnitude will happen. Same thing with earthquakes, more or less along one plate boundary. They will happen at regularly spaced intervals. These are less periodic, but you can tell about how often, or you can tell exactly how often this volcano went off, and from that you can tell about when you'd expect a next eruption. That said, sometimes they go dormant, sometimes they're very active. So I'll just put this first one up. Of stratovolcanoes that you'll read about in your book, and I won't say too much about them, but this is underscoring the fact that you should know about these 3 volcanoes. First, Mount Vesuvius. This was a volcano that went off in 336 before Christ, and it went up. This is not Mount Vesuvius, by the way. I'm going to show you some pictures of it in a minute, just showing you a conical stratovolcano. It grew overnight in the Bay of Naples, not overnight, very quickly in the Bay of Naples. And when it went off with so much ash and pyroclastic debris that it covered a bunch of towns. Has anyone been to this? What's notable about going to Mount Vesuvius? Anyone been there in Italy? Yeah. Excellent, excellent. So that's a really neat thing about this. Sad, horrible. When people came back to survey the damage and look at what happened, I'll go forward to this picture. You can see the villages that were covered over, and you can also, by chipping down into the pyroclastic debris and pouring plaster of Paris into these holes, people were able to get perfect, nearly perfect impressions or imprints of the people that were killed in this eruption. So this is the city of Pompeii, and in the background you see Mount Vesuvius, and it had been destroyed by this huge eruption. So I'll show you a couple of pictures of the people. It's quite a violent way to die if you're in a stratovolcano eruption. When they find remains of people, their teeth are all shattered because the blood in their teeth boiled instantly, teeth shattered, and there are boil marks on the inside of people's skulls because the blood in their brain was boiling. So it's a quick way to die, but it's not a very pleasant way to die. This is a baker in a bakery. And so again, he was covered pretty instantaneously by this pyroclastic debris that came running through, kind of incinerated him, and then you can pour plaster of Paris down, so you're looking at a mold of where he was. There are all sorts, if you Google this, all sorts of sad pictures. This is one of the saddest, I think. I know. It's so sad. It's a dog, right? The dog probably had been asphyxiated by poison gases, but what you can see is he's lying upside down. You can see with great detail the individual pads in his feet. You can see his leather collar here. You can see his canine teeth. So it was with exquisite detail that these things were preserved. You see a young couple lying in bed holding each other. There's a pregnant woman clutching her stomach. Quite sad. Oh, sorry. So that is Mount Vesuvius, and you can see that it was just destroyed. Next one that you'll read about, fascinating case study, Mount Pelée. Mount Pelée is Martinique, and it went off in 1902, killed all 30,000 people on the island, and everyone except for 2 people. One person was a young girl who managed to get away in a small boat. She was found a couple of miles away, and she was unconscious. And the other one was a prisoner in a maximum security jail cell. And the jail was so well built that he managed to escape the heat and the ash and the poison gases. He was horribly burned, and he spent the rest of his days as a circus sideshow freak called the Prisoner of St. Pierre, and he would talk about what it was like to be through this volcanic eruption. But in 1902, we didn't have the predictive capabilities that we have now, and the governor of the island was trying to calm down all 30,000 of his residents, saying, don't worry, there are eruptions, small eruptions, there were earthquakes going on, people were really panicked. He said, don't worry, my wife and I are going to go for a drive up to the summit tonight, and it was pretty ill-timed because he and everyone else died that night. So you read a lot about this, this horrible eruption, 30,000 people dead in 19... And then Mount St. Helens. Let me show you a video of this next class, just a 2-minute clip. This is one of the Cascade Range mountains, which, remember, the Juan de Fuca plate is diving down under the North American plate, and is causing the Cascade Range of mountains, Mount Shasta, Mount St. Helens, Mount Rainier, all of those mountains. And Mount St. Helens has gone off a number of times in the recent past, but in 1980, it went off in a catastrophic way. It sent a cloud of ash and gas 15 miles high, and the cloud started to move on wind currents. There was ash found in 11 states in the United States. It was about $3 billion of damage. So it was a very, very damaging volcano. And the notable thing about this, by 1980, we had gotten pretty good at predicting whether a volcano was going to go off. And we predict, as you'll see, by things like the number of earthquakes and how high up the earthquakes are. So earthquakes that are very deep show that magma is on the move from way down deep in the bottom of the crust. And as the earthquakes become more shallow, the magma's rising up. Earthquakes happen because the edge of the magma cools to the host rock, and you have this stick-slip behavior, which is what an earthquake is. So the shallower the earthquakes are, the more numerous they are, the more likely you're going to have an eruption. And then also sulfur dioxide escape levels. When you start having gases come out, that means the volcano is about to erupt. So we look at things, you can also see swelling at the top of the mountain. Volcanologists look at things to say this is going to go off. So we knew it was going to go off. We knew it was going to be a big eruption, and we evacuated within a certain area those who wanted to leave. Of course, a volcanologist died because he was up there taking measurements, but then also there was a guy by the name of Harry Truman, who was not the president, but he said, I lived my whole life on Mount St. Helens and I'm going to die here, and he did. But the thing is, usually these volcanoes go off straight up. So you have this eruption straight up, like the cartoon diagram that I showed you, or you can look at this. This is in Russia. What goes up? Mount St. Helens went off sideways. And it was a spectacular, spectacular blast. Just obliterated the whole mountain sideways. And so for that reason, you could have almost been on this side of the mountain and not have had anything bad happen to you. But the blast radius that we predicted was much smaller than the actual blast because it went off sideways. So for that reason, 57 people died in this eruption, which is really kind of unheard of, that people would die in an eruption of a volcano in the United States in the 1900s, 1980. So that's Mount St. Helens, and you'll read about that one as well. So we saw Mount Vesuvius. We saw this. So this is not in your book, but I wanted to let you know about the top 5 most dangerous volcanoes on Earth today. Number 1 is right in our country. It's the Yellowstone. We'll see a film on this supervolcano. It's called Yellowstone. Yellowstone, there was a huge volcano that went off back through time, and I don't want to tell you too much about it because you'll see this film. And there are signs that it's grinding up for a huge eruption that would cover about 80% of the United States, at least in some ash. So you'll see this futuristic, really cool film on it. So I won't say too much more about it, but it's in our country, and it would really, really kind of destroy everything. Number 2, Mount Vesuvius in Italy. It has been going off a lot recently. It's one of the world's most active volcanoes, so for that reason, it's one of the world's most dangerous volcanoes. It has an eruption cycle of 20 years, so it goes off about every 20 years. The problem with Mount Vesuvius is that, as you can see, there's about 3 million people that live very close to it, and it's just 5 miles east of Naples. So it is the most densely populated region in the whole world. So this is, I'm sorry, I had the date wrong. 79 AD was the big eruption that I told you about. So there are good things about volcanoes. The good things about volcanoes is the ash that comes out actually makes very fertile, thick, rich soil. So you can grow a lot of food, agriculture, on the slopes of volcanoes or on the flatlands around volcanoes. In Italy, there's a lot of wineries, right? And the wineries come about because of this thick, fertile soil, in part because of volcanoes. So we like volcanoes because they make great soil for us to grow food and wine on. But this is a terrible volcano to be thinking about erupting in a big sense because, remember, something is not a natural disaster unless it kills people. And if there was no one here, it can go off all it wants. But it is going off, when it goes off, around about 3 million people. So we will watch this one closely, and we do. So this one, Popocatépetl, is in Mexico. And this is a situation where there's ash and vapor and earthquakes coming out of this. It's visible at night because the ash is so hot that it's glowing. We'll talk about something called the nuée ardente. So these ash plumes are rising up, and you have all sorts of earthquakes going on in a small sense. But this is also in a fairly densely populated region. And the alert level, we'll talk about alert levels later, is at yellow, phase 2. So Popocatépetl in Mexico, not a good situation. Japan, there was a big eruption. This was back in 2015 that happened right outside of, it's fairly close to Tokyo. And there was a big unexpected eruption at this volcano, Sakurajima volcano. So we're watching this. Again, the problem with the volcanoes in populated areas is that they have the possibility of killing lots of people. So Sakurajima is also one that we're looking at. The last one is in Colombia, Galeras volcano, and it's in southern Colombia, close to Ecuador, and it's been active for a long time. It goes off periodically, and it has, again, the possibility of killing a decent amount of people. Went dormant in 1978, but then just 10 years later started to become active, and we are looking at a big eruption possibly soon. It's erupted every year since 2000, and again, six volcanologists died in an eruption of this not too long ago in '93. So those are the top 5 places to worry about, but the big worry, as you'll see, is Yellowstone in terms of what we're thinking. Another volcano, this is one that maybe some of you have seen. I know a lot of you go abroad to Costa Rica. Arenal is a volcano that is active, and there were 78 people that died in this situation near Arenal in 1968. It erupts a lot. If you've been to Costa Rica, you can go to the hot springs and you can sit in the hot springs soaking in it, looking up at Arenal. And again, the ash that comes out is so hot that the particles of rock are actually still liquid, and at night it's glowing. So you picture this at night, this cloud glowing coming down the side of the mountain. So Arenal is another stratovolcano. With all of these, I'm showing you these. I also showed you Kermisky in Russia. You can see it's very conical, steep sloped, and really kind of picturesque, really pretty volcanoes. So what's the answer to this? Which of these are the most hazardous? Which one would you not want to go off? If you had to rank them, which one would be the worst? Or what top 2? Yep. Yeah, excellent, good. Yellowstone, and then somebody else had your hand up? Yeah, so this is one that we'll see a film on. And also Mount Etna is bad too. We'll see a film on that one because it's quite frightening. So the next type of volcano, that's it, yeah. Okay. Shield volcano. Here's where we have our hotspots that we started introducing the concept of when we talked about plate tectonics. Shield volcano is a very gently sloping volcano. They're called gentle giants for many reasons. So when they erupt, we don't run away from them. We don't have evacuation zones. We like to run to these volcanoes to watch the lava flows. So they're very gently erupting, and they are also gently sloped. This is Mount Kilimanjaro. And they frequently, because they're most alike the composition of the mantle, they erupt oftentimes in the ocean. They erupt underwater. You can see the color of this is very dark. So we're looking at material that is basaltic in nature, most like the composition of the mantle. So it's iron and nickel, as opposed to the lighter colored stuff that erupts on land. And we'll return to a situation when we talk about volcanic rocks later. But they don't erupt in one neck or vent in the center like the stratovolcanoes. They erupt by a diffuse network of fissure eruptions. I'll show you both of these, and gentle lava flows. So it will crack in a spot and lava will splash onto the side of it, or there will be a hole and some lava will come out over here. So it's not one common neck, just sort of diffusely comes out. Some examples that we'll look at are Hawaii. Remember, we looked at hotspot activity from a cursory point of view when we talked about plate tectonics. Hawaii is in the middle of the Pacific plate. And so there shouldn't be any volcanic or earthquake activity there, given our discussion of plate tectonics, yet there is. And then Iceland is also fascinating. It is on that undersea chain of volcanoes in the middle of the Atlantic Ocean, right? It is the seafloor spreading phenomena, but superimposed on that underwater volcanic island chain is a hotspot. So coincidentally, you have a hotspot on a spreading ridge, and it buoys that part of the seafloor up above sea level. So you have this fabulous situation where geographically it's pretty north, and so you have glaciers that you can look at. But tectonically, you have this hot spot, and it's on a divergent boundary, so you have boiling lava lakes and all sorts of hot springs. But 80% of the material that comes out, 80% of the electricity that's generated in this region is from geothermal. So they have free electricity. I was talking about this on the beach the other day with this guy who had just been there. And he's talking about how all the houses are made of metal. They're all metal. And I said, geez, you'd think that in a climate that cold, you wouldn't make metal houses because electricity metal's a conductor of heat. And he said, oh yeah, the electricity's so cheap there that doesn't really matter to them. So kind of neat. So I'll show you pictures of them both. But here is first a picture of lava flows. And you can imagine if you are standing here, you don't feel like there's this tremendous danger to your life. The lava is creeping forward. You can see that there's a skin on it, so it's partially cooled. It's moving very slowly, and someone's standing here taking pictures. Anyway, they would never have pictures of an eruption of a stratovolcano from this close. Two things to note. One, how do you think those trees are faring? They're going to keep growing after this lava flow? Yeah. So you've turned the base of the trees essentially into charcoal. So the big danger with regards to shield volcanoes is that plants and houses and bridges and roads and things that are stationary can get covered over. So anything that can't get out of the way of the lava becomes problematic. Another thing to note about this is that you see that it's cooling from the top inward. And so we'll look later, probably next class, at something called lava tubes. And lava tubes happen when a lava eruption, or an eruption happens, and the outside cools, and it actually insulates the material that's inside. And so the stuff that's inside can flow like crazy because you have this insulated hard shell. So we'll look at lava tubes later. And this is not a lava tube because a tube is exactly what it sounds like. But you can get this concept of the top cooling and insulating the stuff that's coming beneath it. So that's a lava flow. And here's a fissure eruption. So again, this is a diffuse system of erupting. It's not one common neck. And in this fissure eruption, for scale, here's a little volcanologist. He's probably wearing tennis shoes and no breathing protection. He has his little photoionization detector. He's taking measurements of the gas that's coming out of this and maybe some temperature measurements. But you see this crack and the lava is splashing out. And in this way, the volcano right here is growing. So again, it covers over everything. So where there's active eruptions, you don't expect to find any soil, you don't expect to find any vegetation or animals. So we have just kind of like the surface of the moon when you're in this situation. So looking at hot spots, here are the Hawaiian Islands. And what do you notice about this picture? What is this picture supposed to be showing you? What are the different colors representing? Yeah? Yeah, excellent. So you see that Hawaii isn't the same age. So what is going on is if you tip this sideways, the hot spot that we looked at last time is rising up. The plate is here. The hot spot's coming from either the outer core or inner mantle, so it's fixed. It's not being moved by tectonics. But the plate itself is being moved by tectonics, so the hot spot is fixed. The plate is moving. You see the direction of plate movement is to the northwest. So you're essentially burning a hole, because it's not a constant rate, so it'll go fast sometimes and slow down. You're burning holes into the seafloor. You're piling up this lava above sea level, and then it moves away. And two things happen. Number one, when the crust, the lithosphere, is above the hot spot, it buoys it up a little, so you're having an artificially shallow depth. So when it moves away, it will start to subside, it will start to sink down. So you can imagine if it's above sea level, it's going to sink, and so the elevation will get less. But then also, remember from sedimentary processes, anything above sea level is going to be eroded by wind, by rain, by all of these things. So for that reason, Kauai, Oahu, the islands that are in the northwest here are up to almost 6 million years old, and they are eroding and they're subsiding. They're sinking beneath sea level, so eventually those will go away. And when you have an island that's no longer above sea level, it's called a guyot, so just a mound on the seafloor, seamount, things like that. And then as you see, the ages of the island get younger and younger as you move towards the big island. You see it's only 0.2 million years old. I drew this circle here because the big island is actually sliding off of the hotspot right now. We have a new volcanic island that's being formed. It'll peak up above sea level a couple hundred years, is I think an estimate. And we've already named it. It's called Loihi. It's Loihi, and it's the newest Hawaiian island. So all of these other islands are going to erode and go away, dip beneath sea level, and we'll have a big new island in a couple million years called Loihi. So this is a very dynamic, from a tectonic point of view, situation. This is a sideways diagram to show what happens with hotspots, and specifically what happens with Hawaii. So at time 1, there's the hotspot. The volcano is formed. Time 2, this volcano has slid off of the hotspot. You're making a new one. And you see as you go forward, it's eroding, it's sinking down, and it will dip down beneath sea level, no longer be an island. And this is a picture of Hawaii in the last way. You can see Niihau, Kauai, Oahu, those islands are farther away. There's the hotspot. Hotspot's above, again, Loihi now, but there's Hawaii. And the plate is moving that way. The hotspot is from, again, outer core, intermantle, so that's not in the influence directly of the convection cells. So it rises up right through the convection cells and stays fixed while the plate is moving. So right in the middle of the Pacific Ocean. These eruptions, again, are not a big deal. People like to go. You're excited when you go to Hawaii and there's an active eruption. Let's go see it. So a couple of pictures of the surface of Hawaii where eruptions happen. So you can see this sort of splashing out, this diffuse network of eruptions. So I guess that's it. And I talked about Iceland. Iceland will be in the book as well. So Iceland, again, hotspot over divergent boundary, and it is a really, really neat place to go. So the third type of volcano is called a cinder cone. It's also called a Tephra cone. Can also be called a parasitic volcano for reasons that we'll discuss. These are the smallest, and they're also the steepest volcanoes. They don't have any lava associated with them. Sorry. So they are simply pyroclastic debris, broken up fire rocks. And the specific type of pyroclastic debris is lapilli, chunks of pumice. So we'll talk about lapilli later. It's rubble, essentially, bigger than ash in particle size, and ash. And they oftentimes arise very quickly, in a couple of days. You hear this sort of noise, and you have a cinder cone being created. Arizona, New Mexico has a number of these. They just develop quickly on the desert floor. They can form, as we'll see, on the sides of larger volcanoes, and oftentimes they occur in groups. So they're the smallest, they're the steepest. They don't have any lava. It's just ash and pyroclastic debris. And they can arise very quickly, very steep. These are also not tremendously dangerous to your life. They're just associated with larger scale volcanic activity oftentimes. So I'll show you a picture of one. Again, Arizona, New Mexico, good place to find them. You wouldn't be worried about life when you have a cinder cone. They tend to just happen and then they're done. So for scale, there is a 2-lane highway, and you can see it looks like a giant anthill. Also, this material makes for good soil. So you have thick, rich, fertile soil where you have cinder cones. So that's a picture of one. Again, they can happen on the sides of stratovolcanoes. I'll show you a cartoon diagram in a minute of this. So the main neck has the magma rising up, which will shoot out of the vent. But then you can have these little side streamers of magma that come out on the sides, and they'll make for cinder cones, so parasitic volcanoes. They can also happen in the very, very late stage, last gasps of stratovolcano eruption. This is the stratovolcano, Mount Aso in Japan. And the last thing that happened before it went dormant was a little cinder cone formed in the center of the neck. So you're at the top of the huge volcano, and you have this little cinder cone. You'll also have a bunch of them on the sides as well. So I showed you all of these volcanoes in and of themselves on each page. So I wanted to show you this so you can see that there are very different sizes. The first ones that we looked at are over here, the composites or stratovolcanoes. And you can see that they're huge volcanoes, but they are dwarfed by the shield volcanoes. And here are a couple of shield volcanoes, Hawaii, the big island right there. Again, we can see as most of the volume of Hawaii is underwater. There's only a little bit that is above sea level. And some of these, the Guyot and the Atoll, have been eroded beneath sea level, so you're not even seeing them above sea level. And then the Cinder Cone, if I were drawing that, I'd make it even smaller, make a little tiny dot for comparison's sake. A Cinder Cone is a tiny little volcano. We don't worry too much about it. So we'll go back to composite and combine them with cinder cones and see what happens when they go off in a tremendous, tremendous fashion. Those of you who have been to the Cascade Range Mountains out in the Pacific Northwest, I gather, probably been to Mount St. Helens, Mount Jefferson, Mount Hood, all of those. Has anyone been to Mount Mazama? Hiked on Mount Mazama? No, because it doesn't exist anymore. It's really awkward. One time I asked that and someone raised their hand. Yes, I have. No, you haven't. So Ed sort of back away from that. I don't want to call them out as a liar. But anyway, this is what happened to Mount Mazama. It was one of the Cascade Range mountains, and it went off in a catastrophic way. So this is what's going on. You have this huge underground body of magma, and it's rising up towards the surface. You see these fingers. So these would all be little cinder cones here, parasitic volcanoes. It's going off. The volcanic material is cooling and it's rising. You have the stick slip, so there's all these earthquakes, and there's gas explosions for reasons that we'll talk about later, because you're decompressing the material and gas expands, and so you have these huge explosions of gas, earthquakes, volcanoes going off. The ash comes out, ash and lava is coating the thing. Ash is going far, far distances away. So this is a very violent thing going on when you have a huge body of magma like you can see here. So what happens is after the eruption of ash and then lava, it has burst away so violently that the material's carried away, and you end up with a crater. Let me see if there's anything on the slide. Sorry, I usually have my computer up. So you have this crater. The interesting thing when we talk about meteorite impacts later in the semester, geologists refuse to believe the possibility that extraterrestrial material struck Earth. So back through time, when we had meteor crater in Arizona, the Manicouagan crater, the craters from meteorite impacts, we misclassified them as calderas. We said, oh, this was a volcano that went off and collapsed. And we'll talk about geologic evidence in a meteorite crater that's very different than what you'd find in the center of a volcanic crater, but they look the same. So in this case, the volcano just went off so catastrophically, collapsed onto itself, and you can see a little cinder cone forming in the center here. And when the bottom of this crater is sufficiently impermeable, so it doesn't allow water to infiltrate, to percolate through and pass through the system, it can fill with water and become a lake. Doesn't always, but sometimes it does. And in the case of Mount Mazama, which was in the Pacific Northwest, it was replaced by Crater Lake. Anyone been to Crater Lake? So only one person. Fabulous, right? Isn't it the most beautiful place? The water looks like this Caribbean blue. It's so amazing. And so you're driving up, right? And it's like you're going up a stratovolcano, but then it just stops. And there's this field of rubble, all sorts of volcanic material. And you can hike around the rim of this. There's Promontory Point over there, and this little island in the middle is a cinder cone, and it's called Wizard Island. This picture doesn't do it justice, am I correct? The color is just unbelievable. It's in the middle of nowhere. It takes like 5 hours to drive to it from Portland, but it's definitely worth a trip. You see this unbelievable volcano hiking around. You can see the little Wizard Island, collect all sorts of volcanic material, and it is evidence of what happens when a volcano goes off so catastrophically, again, that it can no longer sustain its shell because it just imploded. So you can end up with a caldera. A caldera is a structure it's a collapsed structure related to a stratovolcano. So there's Crater Lake. A couple of other terms here that are associated with volcanoes, specifically with stratovolcanoes. Our first, Noé Ardent, and I don't speak French, but I've been taught as a geologist that this means glowing ash cloud. Those who speak French have said, no, it doesn't. If you speak French, feel free to weigh in and tell me what you think this means. I forgot what someone said. But anyway, the geologic term is for a glowing ash cloud. So what happens is when the pyroclastic debris comes up out of the volcanic neck, again, it's ash, right? It's so hot that the individual ash particles are still actually molten and they're glowing. So especially at night, you can't really see it in the daytime, but at night, you have this cloud coming down the side of the mountain, and it's quite spectacular. If you've ever been to Costa Rica, I've seen this on Arenal or Galeras. The ash cloud comes down the side of the mountain, and it's glowing. It just roars down the side of a mountain. These two are the biggest dangers to your life in a stratovolcano eruption. You might imagine that if you're actually standing up there and a cloud of molten ash and gas comes down around you, you would not fare so well. You would be incinerated. So very, very dangerous. On a stratovolcano, by the time the lava comes, you're already dead. So these are the things that are the big dangers. So New Aerodont, glowing ash cloud. So here's where I said to remember that first picture that I showed you with snow at the top, and you can see in the mountain range there's some snow. If you have a volcano that has snow or it has a big watershed on it, so river system, the ash that comes out will quickly mix with the snow or water, and obviously melt the snow, and now you have a liquid that is the temperature and density of hot cement. So instead of an ash cloud roaring down, the ash is mixed with water, and it's plowing down the side of the mountain. This is a picture of lahars, many lahars, one after the other. So it's like hot cement. It snaps off trees at their bases. It will destroy everything. It will just completely move buildings from their foundation. So yeah, think of just huge amount of hot cement roaring down the side of a volcano. Because of gravity, it will occupy the lowest area, which tends to be riverbeds. You can see here, this is like a riverbed. This lahar has come down and has destroyed everything in that river valley. The first time this happened, it is a volcanic process. So it is associated with volcanoes. The problem here is that every time you wet this, so if a hurricane comes through or if a rainstorm, a very heavy soaking rainstorm comes through, you actually remobilize this material. We'll look at this when we look at landslides. You remobilize the material. As soon as the grains of ash are no longer touching each other, they get sort of hydraulically jacked apart by a lot of water. It's not hot anymore, but it's still like cold cement roaring down the sides of the mountain. And anything that got built in the floodplain since the original eruption, again, will be destroyed. You read about Mount Pinatubo in the Philippines. It went off in 1990. We had an Air Force base there, and we eventually, 10 years later, in 2000, ended up closing the Air Force base because we could not keep the lahars off the runways. Every time there was a storm, lahars just came and covered over the Air Force base over and over and over again. So we just abandoned it. We said, we're done here. So lahars, the first time they happen, again, they're a volcanic process, but remember them, if you will, because when we talk about mass wasting, when we talk about landslides, subsequent wetting is a landslide process. So that's associated with stratovolcanoes. I'm going to go back up to this. We are, 5-6 minutes early. I think I talked fast, but I don't want to start on volcanic rocks now. I want that to be a discrete day. So if anyone has questions, I'm happy to entertain questions. Otherwise, let's end for once a couple minutes early, and I'll see you on Friday. We'll talk about igneous rocks.
I just don't know, will we get like a notification or anything?
Right? Come up with solutions for people. Investment solutions. Dude, work-life balance. What? Work-life balance. Oh yeah? I bet you say that all the time.
That's what I say when it's not
Not important.
I have to go get them. So I will get them, but it's still, we can't release anything.
So if you give them back,
if I order one, the word is slowly degrading.
Okay, thank you. Thank you.
Like if you email, just change what's on it.
Yeah, I sent you an email with the changes, right?
I don't think so.
All right. So if you don't mind, send me an email right now. I wrote it in my list of things to do, and I will absolutely send you that. Apologies.
Okay, no problem. Thank you for taking over.
Yeah, not at all. My pleasure. So I'll go over there now, and I'll input the grades, and I'll just let you know by email.
I mean, I put send a MS Excel sheet on the piece of paper, so it should have just been sent to you.
Did you get the colors? I'm happy to get those.
Yeah, I hand graded.
Okay, all right. So I'll go get them, and then I'll just be in touch on email, and we'll figure out today. All right. I'm heading to Lions. Lions 103.
103. If you just go into the main doors, take a left.
All right. Awesome. Thank you. Awesome. Thank you.